On the bench today, I have a kooky component tester. As you can see here, this kooky tester is based on the popular Mega328 chip. There's many versions of this particular tester floating around for sale out on the internet, especially on eBay. This particular tester is something that I got from Amazon. It came with a plastic case, and I also got a I don't know, a 10 or 20% discount on it, so it made it cost just as much as the ones on eBay, if not a little bit less. Let's open this package up and see what's inside. So I'll set aside, this looks like it's an anti-static bag. I'm not sure if it really is or not, but it looks like one. And inside the bag was this, which appears to be the plastic case. Looks like I'll have to assemble it, and it looks like it's covered in release paper. Here's the tester itself, bubble wrapped inside this plastic bag, so the anti-static bag is kind of useless at this point. And then you can see the tester is wrapped in this other piece of foam here, again kind of negating the effectivity of the anti-static bag, but well, whatever, I'm sure it's fine. So here is the tester itself. You can see there's not a whole lot to the front. There's the component socket, a button of some sort there, and the LCD screen, and some Chinese logo etched into the circuit board there. And then on the other side you can see all the components are mounted, the main processor and some other discretes and active components. As you may be able to see here, I've got all of the parts that were in the kit laid out and ready to go. I've got 4 plastic standoffs, I've got 4 long screws, 8 nuts, 4 short screws, the kooky device itself, and all the pieces that make up the case, the top, bottom, and the sides here. So for the assembly process, the first thing that I'll do is try and peel off this protective coating that's on all of these plastic pieces. I'm going to try and peel this back with this knife blade. So as you can see here, I've got all of the release paper peeled off of the plexiglass here, and I'm ready to start the assembly. It may be difficult to see in this piece of clear plexiglass, but there are 4 holes in it, here, 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 and here, that align to the 4 corner holes in the circuit board. So I'll mount the circuit board here using the standoffs. The other holes that are in the outer edges of the plexiglass are for holding the whole thing together, and we'll use those at the end. So I'm going to use the 4 short screws, and I'm going to put them through the board with the head facing down. So now that the 4 screws are in place, I'll drop these standoffs on. And now I should be able to drop the circuit board on like that. And then I can take a nut and thread that on to each of the screws. As you can see here, I've got the circuit board mounted to the bottom piece of plexiglass, and now I can start assembling the sides. You can see here this thing is sort of set up with, for lack of a better word, I'll call these things mortise and tenon type joints. So now that I've got the sides on, I should be able to drop the top cover on. You can see it's got a cutout for the component socket and the button there. I should be able to just drop this over, line up all the protrusions here to the slots, and should be good to go. So now that the cover is in place, I should be able to just put the rest of these long screws through. And I'm going to put these just like the others so that the head is on the bottom. So once the screw is through, I can then just use one of the nuts to thread on here. We should be good to go. I'll just put the rest on. So there's the kit fully assembled, as you can see, and it all feels pretty rugged. With the cover on, I can activate the button, and I can activate the component socket lock here. So everything seems good. The only problem is that before I put the cover on, I forgot to put a battery in here. So I'm going to need to take it all apart again, put the battery in, and then we should be ready to test this thing out and see how it works. Now that I have a battery installed, I'm going to power this up for the first time and see if it works. And it looks like it's on, so that's a good thing. And let's see, we've got no unknown or damaged part, which seems to make sense. So now I'm ready to test some components. Now, taking a quick look at the circuit board here, it looks like the pins on the socket are labeled such that this column is pin 1, this next column is pin 2, the next one is pin 3, and then subsequent pins are all pin 1. I think I'm reading that right. So what I'm going to start out with first is what I believe to be somewhere around 120 k ohm resistor based on the color code here. So I'm going to throw this in, and I'm going to try and get it between pins 1 and 3, I guess. I'll throw that in like that. I'll lock it down, and now I'll power up the unit, and we'll see what it comes up with. And it looks like it's reading 119.8 kilo ohms. So that's pretty close to the printed value anyway. So next up, I'll try this 1 mega ohm resistor. And I think this time I'm going to go between pin 2 and one of these pin 1s over here on this side. Make it a little easier. Lock it down in place. Fire up the test. And it looks like that is reading correctly, or thereabouts, 1.045 mega ohm, or 1045 kilo ohms. So that looks pretty good too. So now, just for the sake of comparison, I'm going to bring up my Fluke 16 multimeter. This is not the most accurate multimeter in the world. I think this was more designed for HVAC service type people, things like that, but it should work for testing some components here anyway. So I'm going to clip on this resistor and see what we get. So there is the 120 k ohm resistor, and as you can see there, the meter is reading, well, say 121 ohms, so a little bit higher than the component tester. So not sure if that's accuracy differences or if I'm getting a little bit of resistance in the leads here. I've got, well, these are maybe about 2 foot long or so. I'm going to try now the 1 mega ohm resistor and see what I get with that. And that one looks like it's pretty close, right on the money compared to the component test. So next up, I'll bring in my RadioShack meter that I have, and we'll do a quick test on this too and see how it compares. So down here there is a slot to put components in, similar to what's on the component tester. So I should be able to just shove this in and we should get a reading. Now this is not an auto ranging meter, it's a manual ranging meter. But what's nice about this meter is, compared to that Fluke, is that it's got some extra capacity as far as the ranges go. I can go up to 40 mega ohms with this, and I can test capacitors with this, I believe. I don't think I can test capacitors with the Fluke. Anyhow, you can see here that the meter is reading 120.8, so pretty close to the Fluke and still, you know, reasonably close to the component tester. So now I'll pull this resistor out. I'll go up to the 4 meg range and I'll throw in the 1 mega ohm resistor and see what I get. And you can see here it's reading a little bit low compared to the Fluke and the component tester. But it does seem to be sort of creeping up here as I talk. So yeah, I guess we just have to be a little patient, let the meter settle in, and it looks like it's going to be pretty close to the other two. Even if the component tester is not accurate, it's at least consistent with my meters that I have here. Next up, I'll test out this old, what is this, a Rubicon 330 microfarad 10 volt electrolytic cap that I've had kicking around for who knows how many years in my spare parts box. So I don't think that polarity matters on this unit, but I will make sure that I'm going to go between pins 3 and 1. So let's fire this up and see what it reads. Well, as you can see, I've got pins 1 and 3. I've got 339 microfarad. I've got an ESR of 0.05 and a V loss of 1.2%. So all things considered, this should be a good cap. Next up, I'll try and test this little ceramic disc cap. This is probably somewhere in the picofarad range, so lock that down so it gets a good connection, and we'll see what we get here. And it looks like I've got 922 picofarad, so that's a little more than I thought it would be, and an ESR of 17 ohms. So I've brought the Fluke meter back in, and I've set it to measure capacitance. And I don't remember the exact specs on this. This may not be able to check these capacitors. It may have a very narrow range that it can check, but I'll try it anyway. So I'll throw the negative lead on the negative terminal of the electrolytic, throw the positive lead on the positive side, and it looks like we're getting a reading, 360 microfarad. So I think that's a little off from what the component checker measured it at. I don't remember now what the component checker measured. I guess I'll find out when I play the video back, but it did at least measure it, and that's what it came up with. Now, of course, this doesn't measure ESR or V loss, so in that regard, the component checker is way more useful. But at least this does give us an idea that the capacitance measurement is sort of close. So now I'll check the ceramic disc capacitor, and again, I'm not sure if this meter can measure this. This may be too low of a capacitance for it, but we'll try it. And yeah, I think it's exceeded the range. You can see 0.001 microfarad. It's actually close, but it's it's beyond the measurement capacity of this thing. So I've brought the RadioShack meter back now, and I'm going to put the electrolytic in place, and I'm going to observe the correct polarity here if I can. Throw that in and see what it comes up with. Now you can see that the range on this meter is 400 microfarad, so this cap is sort of close to the top end. It looked like it had a measurement there and lost it. So I'm not sure what's up with that. There we go. We got 374 microfarad for a brief minute. I don't know if this thing's going to really be able to cope with this little cap either, but I'm going to send it down to the lowest range, 4 nanofarads, and we'll throw this in place and see what we get. You can see already it's not zeroed out in the first place, so I don't know if this is going to have much effect. I'm not sure the leads are long enough. There we go. And well, it does seem to be measuring something. You can see it's registering about a nanofarad, which if I do the math right, I think that's actually pretty close to the value of this cap. Once again, just kind of like the other one was reading. So, again, we're at the upper and lower ranges of what this meter can handle. So it's not going to really be, truly accurate. So in that regard, and again, because there's no ESR measurement on here, the component checker is, infinitely more useful. Even if the accuracy of it is way off, at least we can kind of get an idea of where the cap is. So next up, I've got a little transistor. I think this is just a 2N222 or some kind of equivalent. It's not really marked on there. Well, there's marking on there, but I can't quite read it. So I'm just going to throw it in here, and I'm going to make sure that I'm across pins 1, 2, and 3 as labeled over here in the socket. Make sure each lead goes into a different slot. Okay, I think that's good. We got that locked into place. Now I don't believe I have to worry about which pin is which on this in terms of which one is the emitter, collector, and base. I think I can just throw this in here and the tester is supposed to be able to figure that out. Okay, let's test this out. And you can see here this is correctly identified this as an NPN transistor. Pin 1 is the collector, pin 2 is the base, pin 3 is the emitter. And it's reading an HFE of 432, and I think is that the forward voltage drop of 672 millivolts. So now just for the heck of it, I'm going to take this transistor, I'm going to flip it over in here. Now one thing I didn't note before is I'm making sure that I'm using pins 1, 2, and 3, but I don't think otherwise the transistor orientation matters. I think the meter is supposed to be able to figure that all out, but just in case I want to flip it over and see what happens. As you can see now it's labeled pin 1 is the emitter, pin 2 is the base, pin 3 is the collector. HFE and the forward voltage seem to be the same. So now I'll bring the RadioShack meter in and give that a test. Now, according to the spec sheet, I believe this transistor is set up so that pin 1 is over here in this orientation, and pin 1 should be the emitter. The middle pin, or pin 2, is the base, and pin 3 over here on the left is the collector. And if I look down here, this meter has a socket for pins to be inserted, and you can see it's labeled emitter, base, collector, and emitter. So if I insert the transistor in here so that I've got my emitter lined up with pin 1, I'm on my transistor NPN test mode, and you can see that things seem to be happening, and it looks like we have an HFE of 0.41, and there's a K there, so I assume that means the decimal point needs to move over, so that would put it roughly in line with what the tester told us the HFE was. And of course this is only measuring the HFE, it's not measuring any other parameters, so it's all we've got to work with, but it does seem to sort of jive with what the tester was reporting. So I think the last component that I'm going to check tonight is this tip 42 transistor. This is something I've had kicking around a long time, but I have the original package for it. You can see it should be a PNP transistor, and the pinout is on the back there, and you can see that with the transistor oriented in this manner, pin 1 is on the left, and according to this chart here, pin 1 is the base, pin 2 is the collector, and pin 3 is the emitter. So I'm going to insert this into the tester so that pin 1 aligns with pin 1 in the test socket, and I'll lock that down, and we'll go ahead and test this and see what it comes up with. So it looks like it's correctly identified it as a PNP, and it looks like it's got the pinout correct. The base, pin 2 is collector, and pin 3 is emitter. And we've got an HFE of 316. And let's retest that. And the voltage rating of 569 millivolts. So comparing to the specs on the back of the package card here, the HFE is 315. It says the minimum HFE for this transistor is 20. But of course that's dependent upon how much current is being pumped through the transistor by the tester. So it's a little hard to really quantify that, but we do know that it's well above the minimum here. Now the forward voltage measurement, at least I think that's what this is, I believe is the voltage drop between the collector and the emitter. I'm not positive of that though. I'm not up on my transistor theory right now. But if that's the case, it is well below the maximum rating here, which you would expect it to be. So I'm not real sure if that forward voltage rating is real meaningful, but maybe that does help understand what the HFE is getting derived from. Again, I'd have to brush up on my transistor theory to really understand that, but it does look like this thing is testing these transistors and able to deal with them and recognize what they are. So I think I'm going to wrap up the video there for now. It's getting a little bit late, but hopefully you got kind of a basic overview of what this thing is and what it can do. And in my opinion, for the $12 or so that I paid for it, it's well worth it. It's a nice handy little device. You can drop a component in there, and it may not be the most accurate thing in the world, but it'll at least give somebody like me who's just more or less just a hobbyist an idea whether a component is good or bad or within sort of spec, I guess would be a good way to put it. I hope you enjoyed the video. If you did, please give it a thumbs up. And if you'd like to leave a comment or subscribe, feel free to do that as well. Thanks for watching.